So today we will discuss about gate strength of materials and wait for a second. So we will start the our class. Yes. See here it is strength of materials. So very important subject, and 6 to 8 marks will come for gate examination. For gate examination, 6 to 8 marks will come. So starting with the strength of material, it is one of the important subject, and it is a base subject for other remaining structure subjects. So it comes in second semester of engineering. So it is very important subject for gate examination. Easily you can score 6 to 8 marks, and straight away very direct bit will come from this subject. So starting with the class, define strength. What is strength? See, there is different definitions for strength, toughness, hardness, ductility, malleability. Okay, so don't confuse between them. So the definition of strength is defined as resistance to failure is called strength. Simply, resistance to failure is called strength, and it is a material property. It does not depends upon load. So strength does not depends upon the load you are applying, and strength does not depends upon the deflection or other characters. So it depend upon the material characteristic. Means with it is made up of which material, what type of material it is made up of, whether it may be wood, whether it may be plastic, whether it may be stone, like that. So it depends upon, it is a material property. Okay, so for we have M20 and FCK is the characteristic strength. Okay, so for M20 concrete it is 20 megapascals, means 20 megapascal means 1 megapascal is equal to 1 Newton per mm square. Okay, one megapascal is equal to 1 Newton per mm square, and FCK is equal to 20 megapascal, that is equal to 20 Newton per mm square. Okay, so similarly M15 is equal to 15 megapascals. So but okay, then what is stiffness? Stiffness is resistance against deformation, is called stiffness. Very important. Stiffness is resistance against deformation. Resistance against deformation. This is a secondary design property. So the first design property is strength, and the secondary design property is stiffness. Stiffness is nothing but resistance against deformation is stiffness. Okay, if stiffness is denoted by K, and if stiffness is more, the deflection will be less, and if the stiffness is less, deflection will be more. That is, stiffness is inversely proportional to deflection. Stiffness is inversely proportional to deflection. Okay, and moreover stiffness is denoted by K, and it has the formula K is equal to load by delta. Okay, it's load by delta. Stiffness is given, it is K is a stiffness factor, and K is equal to load by delta. Moreover stiffness is inversely proportional to deflection. Okay, so assumptions. What are the assumptions in this strength of materials? Entire strength of materials, we have the material is continuous, means continuous means no voids or no cracks, and material is homogeneous and isotropic. What is homogeneous? Homogeneous is if a material is made up of same material. Okay, uh, then it is homogeneous. Isotropic means if it shows same elastic properties in all directions at any point in the material, is isotropic. For example, let the object is like this. So here it is elastic, but here it is inelastic, then it is not isotropic. So isotropic means exhibiting same properties at any point anywhere in the material. Okay, anywhere in the material, so it's isotropic. Okay, okay, so I'll just change the slide. So now yes, we got one more thing. Yes, assumptions. So material is continuous. Okay, already we finished. Material is homogeneous means at any point in direction same properties, means it is made up of same material. Moreover material, type of material depends it defines this property. Okay, So if it at any point the material is made up of same property or same material, so automatically it will exhibit same property at any point. So that is homogeneous. And isotropic is defined as, yes, at any point in any direction, same property. Same property means at any point it in any direction. Homogeneous means in only in one direction. If you go like this in one direction only, it will exhibit certain type of property. But for example, let us say, for example, a rubber is some elastic material like this thing. Okay, a razor is there, so it will expand in this direction but not in this direction, but not in this direction. So this is homogeneous in one direction, means this is homogeneous, but it is not isotropic. Isotropic means exhibiting same properties at any point in any direction. Okay, so that is isotropic. Okay, orthotropic means so no need to discuss beyond our topic. Moreover, orthotropic means at any point in particular direction properties are different. Okay, properties are different at any point in perpendicular direction. Properties are different is known as orthotropic. Anisotropic, all these things are there. Homogeneous, isotropic. Okay, these are all beyond our syllabus, and I don't want these things. Deformation are very small. Yes, we'll just discuss this thing. So, what is deep beam, sinking of supports, torsion, Saint Venant's principle is valid, stress? Yes, coming to this, yes. So, what is stress? Stress is defined as the internal resistance developed against deformation per unit area is called stress. Yeah, for example, if a body is like this, force is applying. Stress is mathematically defined as this force per this surface area. But to be precise, the definition of stress is the resistance developed against that deformation per unit area is called stress. The resistance developed internally. So this is what it is given. The internal resistance developed against deformation per unit area is called stress. And stress is mathematically defined as resisting force per unit area. Means how much force is acting here, that same force this material has to resist. So stress is nothing but resisting force by unit area, and unit of stress is equal to Newton per meter square, because yes, force unit is Newton and area unit is meter square. So force unit is Newton, area unit is meter square, so therefore stress unit is Newton per meter square. Yeah, the important thing is, and in this entire strength of material syllabus is 1 megapascal is equal to 1 Newton per square, because 1 pascal is equal to 1 Newton per meter square, and 1 megapascal is equal to 10 power 6 Newton per meter square. Moreover, if you convert meter square into square, 1 meter square is equal to 10 power 6 square. So therefore, this 10 power 6, that one, okay, I'll write here. Here 1 megapascal is equal to 10 power 6 Newton by 1 meter square. Now 1 meter square is nothing but 10 power 6 square. So this 10 power 6 and this 10 power 6 get cancelled. So 1 megapascal is equal to 1 Newton per square. So similarly, 1 gigapascal is equal to, we know 1 gigapascal in terms of megapascal is 10 power 3 megapascal, and therefore 1 gigapascal is equal to 10 power 3 Newton per square. So these are very important in this entire strength of materials syllabus. So okay, so stress definition of stress is resisting force per unit area, and it is mathematically defined as sigma is equal to P by A. Okay, yeah. So some of the important notes here: a member free to deform without showing reaction or resistance will have zero stress. Yes, because there is no internal resistance, because it is free to deform. Very 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 important. A member free to deform without showing reaction means without showing any resistance, without showing reaction or resistance is given here, without showing resistance or a reaction will have zero stress, because stress is nothing but this force by area. This force is nothing but internal resistance force. Okay, internal resistance to that force. So if there is no resistance in the body, then what will be the stress? Zero. Okay, so it is free to accept. Okay, a member free to move away without any frictional resistance, stress developed is zero. So similar meaning. A member free to expand or contract due to temperature, there will be no stress. Very 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 commonly asked bit in state public service commissions, and even in the gate examination for 1 mark. If a member is free to expand, now free to expand, this is how then, if if any member, not only a steel member or any other member, if any member is free to expand or contract due to temperature change, if you are allowing it for free, then why stress will develop? So automatically the answer is no stress develop. If we restrict the expansion or contraction, then stresses will develop, and that stress is known as temperature stresses. Okay, so we'll go to next slide. Yeah, we have classification of stresses, classification of stresses, and yes, we have here we have classification of stresses. One is normal stress and one is shear stress. Normal stress is nothing but direct stress and indirect stresses. Direct stress we have tension, compression, and indirect stress we have bending or flexible stress because of loading conditions. Okay, so normal, the stress is defined as normal stress and shear stress. Normal we have direct stress and indirect stress. Direct stress means direct tension and direct compression. For example, tie means if you for example, I'll draw here. If a body is there, if we try to pull this body, then this body is under direct tension. Then this body is under direct tension. Or if the same body is there, if we try to compress this body, then this body is under compression. This is the these are direct stresses. So tension and compression. But if a beam or body is like this and we apply load here, and it will subject to bending like this, subject to bending, then the top layer will be under compression and the bottom layer will be under tension. I'll show you how this will happen. Yes, body is like this and we are applying load. Let us say this is some 10 meters, and before applying load, I mean before deformation or before applying a load, so the entire section will be 10 meters length. Here 10 meters, here 10 meters, here 10 meters. But after applying load and after deformation, the body will deform like this. Clearly, if you observe clearly, this part, this part, this part will surely expand, and this will become some 12 meters, and this part will surely contract, this part will surely contract, and instead of 10 it will become some 9. but somewhere between 9 and 12, somewhere between 9 and 12 there exists 10. So 9, 10, 11, 12. So this layer where the length is unchanged, the length is unchanged, the length is unchanged, and that layer is defined as, sorry, that layer is defined as the neutral layer. So means the neutral layer will neither undergo tension nor compression. So the name itself indicates it is a neutral layer. Means we can say almost the layer is subject to negligible negligible stresses are there, but the stresses are very negligible there. Okay, so that is neutral layer. So going back to our slide, so we have yes, we have here, and yes, yes, so this is compression, this is bending, and shear stresses, the direct shear stress and indirect shear stress. So direct is tangential shear stress and indirect is torsional shear stress. We'll discuss all these things in the coming classes. And strain, normal strain, very important. Normal strain. The definition of strain is very important. The strain definition is very important. Strain is defined as change in dimension by original dimension. Change in dimension by original dimension. So let us say the change in dimension is denoted by delta L and original dimensions L. So that is denoted by E. So this is the formula for strain. Very, 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 I mean, very, 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 very important formula. Okay.